Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, Dave Ansell and Chris Smith. We've got a caller, first of all, this evening. Hello to Malcolm in Lowestoft.
Hi, Sue.
What's your question, Malcolm?
Right. This does sound like a trick question, Sue, but I assure you it isn't. A tree falls down in a large forest, but there's absolutely nothing within audio distance, not a living creature. And if that's the case, then the tree, although it makes vibrations in the air while it falls, and it makes vibrations on the ground when it hits, these vibrations can't translate into sound until there's some auditory device like an ear or a microphone to pick them up. And I'd much like to hear their answer.
Oh, that's a good one.
From the point of view of a physicist, a vibration and sound are exactly the same thing. So from that point of view, then when the tree falls down, it makes vibrations, it will make the air vibrate. And so that is exactly the same as a sound. And so, I mean, from my point of view, I'd say that it had made a sound, because it's sort of almost a more deeper philosophical question as to, is there any way of knowing that it made a sound? Basically, if something happens, there's no evidence for it, do we know that it happened? Then that's a philosopher's problem. And I'd rather avoid it. I don't know what Chris thinks about it.
I think there's another angle to this, which is that if the tree fell very, very quietly, so that unaided you couldn't hear it, but you took a very sensitive recording device and then you amplified it so that you made it loud, does that mean the tree's not making any sound? Because it was a sound that your ears couldn't detect. So if I had a very, very, very sensitive microphone here that could hear the tree in the very distant forest,
yes,
and I had a microphone so sensitive that it could hear it from thousands of miles away, would that then satisfy you it would make a sound?
Absolutely.
So the sound vibration energy which the tree is putting into the environment, or the vibrations the tree is making as it falls, that's got to go somewhere. So if it goes into the air and I can pick it up, then it's got to be making a sound. So therefore, I think it's possible to say that you would hear it, because if you had a recording device sufficiently powerful, you could pick that up.
Oh, I agree with that, totally.
I think that answers your question, doesn't it?
Indeed, but what people won't take on board is that if there isn't any such device within any audible range, then the tree can't make a noise.
I think
it's a bit like saying, if there's not a telescope looking at a distant star when it goes supernova, does the light waves it puts out, do they not exist then? And we know that's a fallacious argument, so why should light be any different from sound?
I'm going to think that over.
Malcolm, you're fantastic.
Thanks a lot.
All right, thank you, Malcolm. You take care.
You too, bye.
OK, bye. And this is Sue Marchant, Dr Dave and Dr Chris from The Naked Scientist. We have an email in from Daniel. He says, this could be a very easy question for the scientist, but it's been bugging me for ages. How does a battery charger know when the battery or batteries are charged? Is it something to do with the negativity charged electrons?
The way a battery works is you've basically got a chemical reaction going on in two halves. So a very simple one, which you did in Naked Scientist Kitchen Science a couple of weeks ago. If you put a piece of copper into a lemon and a piece of zinc into a lemon, then the zinc's more reactive than the copper. So you get some tarnish on the copper, which dissolves out, and then the zinc wants to dissolve. But for the zinc to dissolve, you've got to pass an electric current all the way around to the copper. So basically the copper tarnish turns into proper copper, and the zinc oxidizes and essentially turns into tarnish. And to do that, you've got to pass an electric current around the circuit, and that will actually push electrons around the circuit, and you get electric current, and you've got a battery. If you're charging a battery, you have a reaction that if you push electrons in the wrong direction, the reaction will happen in the opposite way backwards. And so you can recharge the battery, the reaction goes backwards, and then when you stop charging it, it goes forwards again. I think the way that battery chargers know things are charged is that the voltage across the battery, when it's really flat, the voltage is quite low, but as it charges up, the voltage increases, and when it gets to a certain point, it's decided this is charged, we won't try and put any more current through, otherwise it's going to break it. So it stops. It just detects when the voltage across the battery gets high enough, and then it stops.
I think a good way to think about this, Dave, is to look at it as like a ball rolling up or down a hill. And you have a hill that gets more and more steep the further the ball goes up it. And so when you're charging the battery, you're pushing the ball up the hill, giving it chemical, but in this case we're talking about potential energy. And as the battery gets more charged, the voltage that you need to push the ball further up that notional hill gets higher and higher because the hill is getting steeper and steeper, so the battery charger has to work harder and harder to get the ball up there. That's because it's pushing the chemical reaction backwards inside the battery, and eventually the chemical reaction is completely reversed, so there's no more chemicals to go backwards, and that's when the hill gets infinitely steep, and the battery charger can detect that, and that's when it switches off, when that voltage gets very high.
Right, I think that's rounded it up nicely. Thank you very much, Dr. Chris. Gary sent a text in to say he's going on a plane for the first time. And why do we get worried about new things, he says, and how can we get over it before it happens?
I think it's because we're programmed as human beings to be cautious. We had an item which we ran on the Naked Scientists, and it was a study by a lady called Sarah Heil-Bronner, who's a researcher at Duke University in America. And she's been trying to answer the question about why it is that humans, if you give them the opportunity to gamble, tend to take the conservative option. We tend to take the safe bet and avoid gambling if we can, for the most part. Obviously, some of us are a bit more adrenaline junkified than others. But the way she tried to get at the evolutionary origin of this question was not by looking at us so much, but looking at our closest relatives. She was looking at chimpanzees and bonobos, and they're very, very closely related to each other, but they're also very, very closely related to us. Now, chimps and bonobos obviously don't understand the value of money, but what they do understand is the value of food. And so she gave them a choice in this study. She had 5 chimps and 5 bonobos, and in sequential trials, they were shown 2 upturned bowls. And under one coloured bowl, it was always the same colour, there were always 4 pieces of grape, which is pretty high-value prize for a bonobo or a chimpanzee, because they like fruit. Under the other bowl, there were, and that was the high-risk bowl, there was either 1 grape or there might be twice as many grapes. So they knew pretty quickly by learning the trials that if they picked the red bowl, let's say, they were always going to get a reward and it was always going to be a good one, 4 bits of grape. On the other hand, they could choose the blue bowl, and under that there would be sometimes a very, very big reward, but sometimes something that's virtually not worth having. So when she asked the chimpanzees to do the experiment, they always chose to gamble. They always went for the high risk, whereas the bonobos always went for the low risk. They always chose the surefire reward. And the clue to why they did that's in their evolutionary origin. The bonobos, when they grow up, they live largely in jungle areas where fruit and food is on the ground level. There's lots of it, and they virtually never have to compete for food. So they always know where their next meal's coming from. Chimpanzees live up in the trees. They rely often for their nourishment on catching colobus monkeys and eating them. And this is a very high-risk practice. They might not get fed some days. They might get a very rich meal another. So their evolutionary origins say you should gamble. Now, humans, of course, have learned that we can basically get food when we want it by being ingenious. And so our conditioning, our evolutionary conditioning, has been to play safe. So we tend to be quite conservative about a lot of the decisions we make. And that means that when you're faced with novelty, a new situation, you compare that in your mind to the existing situation, safe situation, or I can do something adventurous. And you tend to default to, I prefer the safe option. We all prefer the easy life. Why do we make life hard for ourselves? Because we are really risk-averse as a whole, as a species. And going on an aeroplane or doing something entirely novel if you've never done it before is a bit scary. And so some people do find that scariness is worse for them than perhaps other people. Perhaps they just weigh the situation up differently. And as a result, their evolutionary origins are kicking in and saying, be cautious. And so it's just basically human nature. And in fact, it's not just human nature, but it's chimpanzee and bonobo nature too.
So it depends how many grapes you like, really, in a way, doesn't it? Anyway, we have got Mrs. Wright from Beccles on the phone. Hello there, Mrs. Wright.
Hello there.
Hello, you're through to Dr. Chris and Dr. Dave.
Okay, thanks very much. I've got a question on anatomy. White adults, females, have, I presumed it was everybody in that category, has a brown line from their belly button downwards, straight line. And I wondered if you could tell me what the name of that is. That's
called the linea nigra. Linear line in Latin, nigra, black in Latin.
Yes.
And it just goes vertically, as you say, from your umbilicus, your belly button, down towards your pubic bone.
Yes.
And it's well known to people who see their obstetricians because it often gets a lot darker when women are pregnant.
Yeah.
It's lovely talking to you. Thank you very much for your question.
Right.
Right, Dr. Dave, it is just you and I.
Indeed.
Now we've got Jill on the line. Hello, Jill.
Hi, Sue.
How are you?
I'm not too bad, thank you.
You've got Dr. Dave.
Hello.
Hello.
Well, I'm a girl, a lady that collect cuddly toys.
Yeah.
I should imagine within a year or 6 months you would have to change the battery. Now, I've got this duck that will squeak and that will do anything, and I've had this duck for about 15 years.
Have you got it there?
Yeah.
That is just amazing, it really is.
Now,
right, okay,
my question is, why is it going on for about 15 years and the battery has not gone out? I don't understand.
Do you use it very often?
Cosmic.
Well, yes. Every time I go upstairs, I've got about 200 cuddlies.
Have you? How fantastic.
This one,
yeah.
I don't know why it goes on. I suppose the scientific question is, why is this battery going on for that thing?
Jill, what sort of battery is it?
I don't know.
Have you not looked inside it?
Well, no.
Okay, so where does there must be a battery in the duct?
Oh, yeah, I can undo it if you like.
All right, okay. What sort of battery is it?
The Duracell. There's just two.
Two?
Two wires, the black one and the red one.
Okay.
So you're using it every day and it still lasted that long?
Well, no. I've got other cuddly toys that makes noises.
Yeah.
And they've actually gone within a year.
Yeah, I mean, fundamentally batteries can degrade in other ways, especially if they're quite discharged. They can rupture after a while because the contents of them are quite nasty and they can actually dissolve away the casing. But if that doesn't happen, and especially with sort of alkaline cells, the sort of cells which Duracells are, they don't discharge themselves very quickly. So as long as you're not using them, then they will last several years, certainly. 15 is pretty good going.
Years. 15 years old, Doctor.
I think you're probably just very lucky. You happen to have got a very, very good battery, just probably by fluke. They happen to have made one which will last particularly well, and you haven't used it that much. It just is still going.
Val, thank you ever so much, and it's fantastic. Look after that duck, because I think it's a bit special. Take care, darling.
Thank you.
OK, bye.
Bye.
Dr. Dave is here in the studio with me, answering questions. And Gary has called in to say, I've heard that most of the universe is made of dark matter and dark energy. And he says he understands dark matter, but what is dark energy?
Again, it's one of these fundamental ones that no one's really completely sure. But basically, dark matter is basically what happens is astronomers and cosmologists look at the universe. And they look at the way stars are behaving. Start off with dark matter. If you look at a galaxy a long, long way away and try and work out how much it should weigh from all the stars in it, and you add up all the weights in all the stars. If you add up all the weights in the stars, you get a mass. And then you look at how fast things are orbiting it. And then they seem to be orbiting it much faster than they should be for that mass. There's more mass there that we can't see. So what people hypothesise that there's a load of matter there somewhere which is dark, which we can't see. We don't know what it is. People have suggested it may be dark planets, but I don't think there could be enough of it there we've noticed.
When you say dark, does that mean just a black mass of something?
By dark, it means it's invisible.
Right.
So because most of the stuff we can see matter in stars.
Yes, okay.
You can see some things which isn't even things like gas glows at glows, but in the sort of radio waves. So if you build a radio telescope, you can see even quite cold gas. I mean, you'd be glowing in the infrared, and even something much colder than you, even stuff a few degrees above absolute zero, so really, really cold, minus 270. You can see it glowing very, very gently in the radio waves.
Yeah.
But various dark matter things, there's all sorts of particles there's definitely particles called neutrinos, which don't interact with light at all. They only interact with the very centres of atoms and nucleuses, and then very, very, very rarely. So they only interact with the universe much in the form of gravity. And they're very, very light though. But people have hypothesised there are other particles which would only interact with the rest of the universe by gravity and not by anything else. So maybe the dark matter's in some kind of strange particle, or it could even be that we don't quite understand gravity right, and gravity just behaves slightly differently to the way we think it does on a really big scale. Now, dark energy is a similar thing that you kind of have an observation, you're trying to explain it by something. If you look at the universe as a whole, you'd expect something exploded, and then because it's really heavy, gravity should be slowing it down over time, over billions of years, and things should be slowing down as the universe expands. But it seems that definitely at various points in the universe's past, and possibly even now, the opposite's happening. The universe seems to be expanding, and it's expanding faster with time, so it's accelerating. So some energy is coming from somewhere. And so it's like, as if you get that universe expand, energy's coming from somewhere, and people kind of, because it's something we don't really understand, people are calling it dark energy. People are even less sure of what dark energy is than they are of dark matter. It could just be the way the universe works. There's something called the cosmological constant, which comes out of a load of Einstein's equations, which if it was there, then that would have a similar effect. It would release energy as the universe gets bigger. Or it could be something entirely different we don't understand. Yeah, I mean, basically, it's just something trying to explain a load of observations about the way the universe expands, which we don't kind of make sense according to physics as we know it.
Whoa, that's quite something. It's got me thinking now. Dave says, why is there a time delay on DAB radio stations and not on normal FM? Steve in Basildon.
Basically, normal FM radio station, the electronics to transmit it don't have to do very much work. Sound, as I speak into this microphone, is a vibration, then that forms a vibrating electrical signal at a fairly low frequency. Then that vibrates the frequency of the transmitter, which it can happen in sort of probably a millionth of a second. The electronics is very, very quick, so there's no delay. But if digital radio, because you're trying to squeeze as much information into the radio waves as possible, so you're trying to use up as little space as possible with your radio station. So it will do things like, if there's two noises going on at the same time, which your brain couldn't hear the second one, which is quieter or a similar sort of pitch octave above, your brain assumes it's there even if it's not. There's all sorts of cunning things whereby the digital electronics inside the transmitter will kind of say, that's not important, I'll ignore that. And it'll kind of compress it, and it will kind of make guesses. It'll kind of, if sound normally does something, then it will assume that's going to happen and throw away the information. So you can squeeze down the information. You have much less information to transmit a radio station. But this process takes time, and it seems to take a second or two to be able to do this, partly because it's got to look over a second to be able to do all the calculations, and just the calculations take a long time, and then the decoding it on your radio takes a while. So the whole process, just because it's doing more work, it takes longer. And it actually also takes more power, which various people have noticed, which will probably get better as the electronics gets improved and electronics improves generally, but it's intrinsically doing more work, so it's got to take more power and more time.
Now, here's one here. Science question. What is, and it's Syzygy, is Syzygy, and that was spelt out too. Steve, any ideas?
I have to admit that my only reason why I have any idea for this is thanks to the wonders of the internet.
Yep.
It would appear to basically be a name for, basically if you get three planets or moons or planets in the same kind of planetary system lining up in a straight line, which isn't so kind of, I mean, if you had the Earth, Moon, and then Sun on a line, or the Earth on one side, then the Sun, and then the Mars on the opposite side, or whatever. I don't think it's especially interesting from the point of view of actually science, apart from if you get something like, recently there was a Venus transiting across the Sun. If Venus get between us and the Sun, then the Earth, Venus and the Sun have to be in a straight line. You can sometimes find out interesting things about planets' atmospheres, because you can look at the light which is going through the planet's atmosphere from the Sun through the planet's atmosphere to Earth, and you can look at, by using a thing called spectroscopy, if you look very carefully at the light and what colours of light are missing when it's gone through an atmosphere or something, you can work out what was in the atmosphere. So I think it probably meant you could find out what was in Venus's atmosphere long before we went there and actually could look. But otherwise, I think mostly it's considered interesting from the point of view of astrologers who like that sort of thing for reasons I've never quite understood.
Yeah, it's because we're cosmic, you see. All right, so a couple of little questions here, David. Somebody's going to have a mechanical valve to replace an aortic valve. Will it set alarms off at airports when they go through scanners?
I think you've got to have quite a large... I mean, the scanners in airports are kind of tuned quite carefully to... They don't tend to pick up very small pieces of metal. And I wouldn't have thought you need a very large lump of metal to make a aortic valve I don't know what exactly the design... I think there are various different designs, and they could involve quite a lot of plastic. I would get a letter, if it's involving large lumps of metal, I get a letter from your doctor, because it may make getting through airports easier and less unpleasant.
Sure.
I think the frequencies which they're using to look for tend to get attenuated by your body a bit anyway, so if it's inside you, it would be less of a problem than if you're carrying it around in your pocket, but I don't know for certain, so...
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.